So my name is David Cavuto. I'll get to my slide deck in 1 second. Be aware, I am running stream on the Wi-Fi right now. Everyone should look down at their devices and question what they're doing. Okay, so having given you that disclaimer, we will get into the deck. Again, my name is David. I've been with Splunk for 6.5 years. Today we're going to be talking about service and asset discovery with wire data. For those who are familiar with Stream, this conversation is going to be about, let's say 60%, 60 to 70% on Stream background and wire data, and about 40% on actually how to do the discovery part. So if you are a Stream novice, that's good. If you're a Stream expert, you might be bored for a little while. So just quick show of hands, who has used Stream? Splunk Stream? Okay. Who's used wire data in general? Opened up Wireshark, looked at TCP dump. Okay, good. All right, good enough. Fair enough. Okay, forward-looking statements. I'm sure you guys are sick of this. I'm not going to go into it. All right, so my bio, just so you know, I have been working in computer networks and computer network security for about 23, 25 years. I was fortunate enough to start officially at Bell Labs, which is an electrical engineer's dream. A great place to go, a great place to work, especially back then. I worked with folks like Bill Cheswick, Steve Bellovin, David Korn, really sort of the peoples whose names are on the books on my shelf, which is absolutely cool. It was really interesting to be able to say, hey, I have a question on the IP or on C++. I'm going to go ask Bjorn Strustrup because he's like, right down there. Very rarely does an engineer have that opportunity, so it was great. I was really lucky to be able to do that. I worked at AT&T for a while in network security on the CSO project under Ed Amoroso, and then I left to join a small company called Norris that did packet analysis and packet forensics. From there, I moved over to Splunk, and I've been at Splunk, for, like I said, for about 6.5 years. So I've been going back and forth between vendors and service providers, and so I have kind of a broad variety of experience on, as I said, network analytics and security specifically. So today what we're going to talk about is wire data, but specifically how to use wire data to find stuff out. It's always occurred to me that if you really want to know anything about what's going across your network, you should really understand your wire data. You should look at it. I used to carry on a piece of Cat5 cable. I would wave it around at conferences and say, hey, does everyone know what this is? Everyone goes, yes, sure, it's Ethernet cable. And then I said, all right, what's on it? To a resounding silence. And that's really the point, is that it's really easy to plug two things together. It's often very difficult to understand what is going across that communication. So trying to understand what's on your network is really, I think, a critical aspect of any network operations. And it's actually the first element of security. CSC number 1 is network and host inventory, trying to understand what is on your network. And I cannot tell you how many customers I've gone to, and when I say to them, okay, what's your network inventory look like? They point me to Active Directory. I say, well, what's your service inventory look like? Again, silence. What's your service inventory policy? What's your policy in terms of what you're supposed to be running on, what your users are allowed to run on their machines? Again, silence. So it just sort of raises the sensitivity to folks that really there's a lot of failure to understand, failure to observe even what is happening. So like I said, we're going to spend some time on Stream, some wire data. Then we're going to go into asset host discovery, service discovery. And there will be a demo, no question mark. I spent some time, and as I said, Stream is running right now. And it's on the Conf19 network. So if you have a machine connected to the Conf9 network, you will be scanned. Well, captured. But we'll talk about that in a minute. All right. So problem statement. I cannot see this at all from over here. Okay, that's better. Right, so it's easy to add assets to networks, right? People can plug things in, DHCP, Wi-Fi, open guest networks. We let them do it. We make it easy for them. I have been at exactly one customer in my 6.5 years at Splunk, where I turned on a machine, connected it to a network, and suddenly, within literally 5 minutes, somebody was over here with a Fluke LAN meter and said, hey, did somebody turn on a laptop? And I was damn impressed with them. If you ask me afterwards, I'll tell you who it was. But very Infrequently does that happen. Usually the common mode is people have no idea what's connected to their network. And often that's to their detriment. It's to your detriment, it's to our detriment. So we make it easy. Services can also be added to networks, right? People run computers, people add software to those computers, and we, as technology experts, may know what's running on that software, but the layperson probably doesn't. But we issue them computers and we often allow them to install software on those computers. How do we know what they're doing? How do they know what they're doing? Should they? Should we? As network administrators, as security professionals, as IT operations staff, should we understand, should we make an effort to really understand what they're doing on our computers, our networks? How can we manage the assets if we're not aware of them? I'll tell you a funny story. I was a consultant in my college days. I worked my way through college doing computer consulting in the late 90s, or in mid 90s, I suppose. Feeling old now. A great time to live in New York City, make all sorts of money doing really fixing Microsoft Word for people who didn't know how to use it, which was great. And it would pay me lots of money. But one of my customers called me up and said, those fateful words, "We can't see the internet." That sounds like a problem, okay? So I tried to SSH into their router remotely, and I got a login prompt that came back at about 1 character every 3 seconds. Oh, and I was like, that's not a good sign. Router's pinned at 100%, nothing's going through. Did some surveying, finally figured out that every machine in their 300-person building, or 300-person office, was spitting lots and lots and lots of traffic out, TCP 500. And this is before the days of IKE, so it wasn't IKE. It was just garbage. Now, it turned out it was a 0-day. We captured it, we isolated it, sent it over to Virus Total. No one had ever seen it before. Very cool. When we did a little forensics on it, we found out a vendor had plugged a laptop into their switch physically, in their server room physically. And I said, who allowed this to happen? And no one answered, no one fessed up to it. But that was the source of the problem. Immediately, some malware on that machine propagated across the network. Now, setting aside for the fact that maybe the vendor shouldn't have been in that room connecting something to a patch panel, maybe someone should have noticed that happened. Maybe there should have been an alert. It wasn't like they were scanning on Wi-Fi. They physically attached a machine to an Ethernet switch. How do we manage these assets if we're not aware of them? So that's where wire data comes in. I love wire data. I'm a huge fan of wire data because it cannot lie to you. Log files can lie. How can log files lie? Well, the people who wrote it may have misrepresented what's supposed to be in them. Now, developers are all very upstanding. We know that. No one's going to say anything bad about developer staff. But maybe they made a mistake. Maybe they sort of said, that update interval was 1 second. And they hard-coded the 1. Happens. Maybe they forgot to log something. Maybe an adversary got in and modified the logs. That happens more than you think. So what I like about wire data is it represents the ground truth of what happened on your network. It cannot be lying because it already represents what the conversations were. You may not see it, it may be encrypted, it may be obfuscated, but it cannot be lying, which is what I like. So if there's traffic, that traffic came from a host. Now, certainly the host could have lied about its source address, yes, but that traffic originated from something. It did not materialize out of the ether, even though we call it Ethernet. So it's really an authoritative record of the conversation. Everyone familiar with this? The OSI stack? Great, I'm not going to go into that. Super duper. Okay, so what I like about wire data in the scope of the problem space of network and host and asset discovery. No, that's not right either. Asset and service discovery, that's right. Is that you see the traffic. If the traffic is on the network, traffic came from a host, and almost certainly that host didn't spoof its source address. Well, let's hope it didn't. We can talk about that later. But if we're seeing at least 3-way TCP handshakes, that means traffic is being routed to and from the machine. So there's a good chance that machine is on your network somewhere. Same thing with TCP connections. if you see a connection-oriented protocol destined to a machine, and that machine answers, it's running a service that's listening on that port. Then the question is, should it be? If your neighbor has TCP traffic destined to port 25, he is running a mail server, most likely. The question is why? Now again, we'll talk about spoofing services in a minute, but should his machine even be listening on port 25? But we can tell without putting a single piece of software on his machine, without having any control over his machine whatsoever, because we see the traffic. So that's why I'm a fan of using wire data for host inventory, for service inventory, because it does not rely on cooperation from the endpoint, which often you don't have. All right, so with Stream, and we'll talk about, this really should be in the Stream section, but so any wire data collection sort of works like this, right? We're capturing data that's going across between the endpoints. It's got to potentially decrypt traffic, it's encrypted, and it's got to do protocol decoding, also known as deep packet inspection, but it also really has to reassemble the conversations. At some point, looking at raw packets is a bit much, so being able to stitch packets together into conversations is really quite useful. But it's also super critical if you're doing host discovery, because you really want to understand where the endpoints are. A TCP conversation initiated outbound from your network is very different from packets that happen to have a source address or a destination address that are on your local network. Right? A source address on your network just means a packet was sent from, but does not mean the conversation was initiated from. Right? So the statefulness of the connection was important. Right? Back in the days of stateful packet filters, that was sort of the only way we had to discriminate inbound connections versus outbound connections. But understanding that your connections are stateful, generally speaking, if they're TCP, helps this whole process. So anyway, let's talk just a little bit about Stream. Again, OSI stuff. Important to know that Stream, and the blue is a little bit optimistic, Splunk Stream, so again, I mentioned Splunk Stream. Let me just give you the quick 30 seconds on it. Splunk Stream is Splunk's wire data capture solution, generates metadata. I have a one-page slide that talks about it. But main difference between other collection technologies, especially things like NetFlow, is that Stream is operating all the way at layer 7. So with NetFlow, you get IP addresses and ports. Good to have. And if you have nothing else, by all means, use NetFlow. But since Stream is available, it is free. That is, there's no charge for the app. Of course, there's data, and you have to pay for the license. But, one thing I want to mention, there exists a reduced rate Stream license. If you are interested in Stream, and if you're interested in especially putting a lot of data in Stream, ask your sales manager about a reduced rate license for Stream. Okay? There's also new licensing models for Splunk. We talked about some of them already, vCPU license, et cetera. Some of those will apply, right? So a lot of the resistance to people using Stream has been, oh my God, it's going to blow up our license. But there's like 6 ways to avoid that. We'll talk about that in a little while as well. But anyway, so Stream gives you the application layer. So Stream will give you layers 2, 3, 4, and 7. And that's super important because you need to understand, especially if you're doing service discovery, what is going on the application layer. Just because it's TCP 443 does not mean it's just web traffic, right? Everyone's overloading the port. Let's try to understand more specifically what is happening on it. Okay, so here's my one-page everything that Stream does slide. How am I doing on time? 30 minutes? Okay, good. I'm going to try to get through the slides in another 15 minutes, and then we'll talk. And then I'll show you the demo. All right. So what does Stream do? That was 2 bullet points, but okay. Stream does packet metadata collection, right? So it's observing packets. It's reassembling packets into conversations. It is recognizing dynamically the application layer protocol. People don't know it does that. It is parsing the application layer protocol for the 30 some odd protocols that it understands. And then it is generating metadata. What is metadata? Well, they're key value pairs that are either exactly extracted from the protocol, like HTTP headers, SMTP headers, things like that, that have a value that have a key or a parameter name in them. It's giving you the exact parameter name as a Splunk field and giving you the exact parameter value. Or for other protocols where the field names are not in the protocol themselves. They're in the RFC, things like DNS or SSL. We are trying to, as often as possible, use the same field names as in the specification. But if not, they're often quite similar. So inside stream events, you are getting field names that are really match what's in the protocol. But keep in mind, in a given conversation, you may have many packets in many directions. Stream events give you, generally speaking, one event that represents the entire conversation. So think of an email, right? You have SMTP, RFC 2821 traffic going back and forth, and there could be lots of packets in each direction. Stream parses all of that, reassembles it, and gives you a single event that has all of the layer 3 data, so IP addresses, all the layer 4 data, TCP information, and it's going to give you the layer 7 information. So it's going to give you sender, recipient, subject line, message body, transfer encoding type, MIME type, things like that, attachment names, attachment sizes. So Stream can do all of that. Super cool. So new feature as of about 2 years ago, which was the most recent version of Stream. By the way, Stream has a new product manager, so a new version of Stream will be coming out soon, which is cool. Stream can now do targeted packet capture. And by what we mean by targeted is if you specify a parameter, a field name, so an IP address, a layer 7 parameter like an email address, it will capture individual conversations at the full packet layer and sessionize them, put them into PCAP files, and drop them into a NAS for you, which is really useful. So you can say, all right, I want to capture all of the metadata for SMTP, but if any emails happen to have .hacker.com in them, I would like to capture the full content to a PCAP file. It will do that. And note the coolest part of that, it will have buffered the previous packets. Because where does the SMTP address appear? In like the 14th packet of the conversation, right? It ain't in the first one. But Stream buffers all the way back. So when it finds a match on a parameter that you've specified, it has buffered all the packets all the way back. So you get a full TCP all the way back to the original, a full PCAP all the way back to the original TCP handshake, which is cool to me. Some people like some things. I like packets. All right. And it'll also extract files, if you're interested in that too. So if you're sending a file via SMTP or HTTP, it will pull attachments out of that and save the attachments to your NAS as well. It does NetFlow, so Stream is now our official NetFlow collector. So Stream will do active NetFlow collection. You send NetFlow to it. It will not do it passively, but it will do it actively as a collector. It does about 165,000 NetFlow events per second on a 12 by 12 machine, 12 cores, 12 gigs of RAM, which is pretty impressive, and you can have as many as you want. So if you need 500,000, no problem, install 3. It does estimate mode, right? Which means if you don't know what's on your network, install any Stream in estimate mode and it will cost you nothing, no license impact whatsoever, and it will tell you how much it would have affected your license if you had turned it on. So people always say to me, hey, I really like Stream. Stream is great, but we can't afford Stream because it uses up so much of our license. Bull. Put it in estimate mode. Figure out exactly how much of your license it's going to use, and then tweak it. It does commercial application detection, so in addition to the 30 protocols it fully parses, it has about 300 protocols that it will detect, all like port 80 and port 443 detection. So it won't just tell you, oh, it's port 443, it'll tell you it's Facebook or Pornhub. That's a useful distinction to know what your users are doing. It'll decrypt traffic if you have the certificates. It does aggregation. So just like now we have DSP, right, for manipulating data on ingest on any Splunk forwarder. Now, and you've always been able to do it on Stream. So this is another way to reduce data ingest on Stream. If once your first step is aggregate mode, and I say, that's interesting. I see a lot of data that I'm quite interested in. I'd like to collect more of that, but I don't want so much that it blows up my license. You can aggregate. So you can have Stream do aggregates of inbound data. I want to just say, for every source IP, destination IP combination, I want just counts of packets, or sum of packets and distinct applications. You can do that, and I'll demonstrate that for you. Whoops, wrong button. It does filtering endpoints, it has a lot of out-of-box content, and you can manage the forwarders. Okay, that's all you get about Stream. These are the protocols that are in the application. There will be a new release within a month, I am told by the new product manager, with new protocols, which is quite interesting. Commercial application detection, we mentioned that. Here's the eye chart. This is intended to be funny, you may laugh. Okay, great. Thank you. But here are the categories that we support for those commercial applications. So we picked a smattering of what we thought was sort of interesting applications and made those our application detection. Okay, cool. So now we're into the 23 minutes, great. We have all sorts of time. We're into the section where we talk about really the point of this discussion, which is how do we do discovery. So suggestions, and this is a little bit, again, optimistic, but where do you want to put stream forwarders? Well, the point here is that you can and may put them anywhere you want. Because Stream is free and easy to deploy, put it wherever convenient. You can put it on hosts, you can put it on networks. Not everyone understands that Stream was designed specifically as a cloud-based monitoring solution. So you can put Stream directly on hosts that are running servers. Right? Put it on your web server, put it on your DNS server. Stream will happily monitor that traffic. It connects to universal forwarders, it connects to heavy forwarders. But if you have a UF on a machine, you want to monitor packets on it, you just throw the Stream TA on it, and it will capture packets to and from that machine. Now, only to and from that machine, it doesn't put the interface in promiscuous mode, but it will generate Stream data to anything destined to that machine. So that's a helpful way to monitor machines that are VMs that are in the cloud, that you don't have physical access to the infrastructure. Easy to use. All right, so how do we do interesting host and application discovery with Stream? Well, or with any wire data. So everything I'm going to be talking about really has to do with wire data. I may go back and forth between wire data and Stream, but really just assume when I say one, I mean the other. If I am using a Stream feature specifically, I'll call that out. So first thing is simply harvest, right? So you see traffic and you collect information. The analog I like to use is, let's say you're standing on a highway overpass. You can watch traffic pass you, and you can note its characteristics. Hey, there's a brown car, there's a blue car, there's a green car, it's a Honda, it's a Porsche, it's a Chevy, it's a Tesla. We just got a Tesla, by the way, very exciting. So you can note characteristics of the traffic as it passes, and it is entirely passive. The traffic is not aware that it has been observed, which is useful. The traffic cannot prevent you from observing it, also useful, right? So they can't hide because the traffic is going across your network. So harvesting data really consists of looking at traffic as it passes and collecting salient aspects of it. Number two, enriching. So you might want to add information, like if it's an IP address, add an FQDN, do a DNS lookup on it, right? You can store that persistently, and it's probably important to do at the collection time because DNS may change. If you have dynamic DNS, if you have dynamic IP addresses, you don't necessarily know now what that IP address was then. So you might want to do enrichment at the time of collection. You might want to add geoloc information. You might want to add service name. You might want to add any information that you happen to have. If you have a CMDB or a DBOR, you might want to pull that information out and stamp it onto the information at the time of collection, not later, because, again, it may change. And finally, alerting, right? So the way I often recommend people do this is start harvesting, start collecting, generate sort of a base data set, and then maybe after a week, after 2 weeks, turn on alerting. So for example, let's say we started collecting all the source IP addresses in, I don't know, the room, this room, right now, which I'm doing. That list is going to keep generating, and it's going to keep getting bigger and bigger and bigger. I'm doing it once a minute. So every minute, I pull out all the source IP addresses of the last minute that I saw of all the packets that it's observing, and I throw them into a CSV file. Real easy. Right? And I just note the time that it arrived. The next minute, we pull out the same data and match it against the previous set. If it's new, we just add it to the bottom. If it's old, we update the timestamp and say, hey, we saw it again. That's useful for two reasons. Number one, you say, I can say when things are new, right? After a week, after 2 weeks, I should pretty much have all the hosts on my network in my file. Suddenly a host shows up like a guy plugging in that switch, and you can generate an alert. Because suddenly that thing is new. Your network should be fairly static. Most people don't generally have many hosts being added to it day after day. Now, you may be an exception. That may not work for you. But the point is, collecting the data and noting when changes happen is interesting. All right, let's see. So, asset discovery, how are we doing on time? Okay, good. There's like 4 more slides and then we'll do demo. All right, harvesting assets. So, as I said, host IP address for every packet. Important to know what packets to look at, right? So, I am doing right now simply IP, TCP, and UDP. That's it. I'm looking at layers 3 and 4. But you could easily pre-filter that. You could use higher layer applications. Things that really work are ARP, DNS. I should have put DHCP there as well. Those are great for a variety of reasons. DHCP tends to be sent with local broadcast, all 255s, so you'll tend to see it on every station. You don't need to be in promiscuous mode, or you don't need to have a span port to grab it. That's why this works, by the way. Not all of your traffic is going to every one station, but multicast DNS is used everywhere. Right? On Macs, especially, the Bonjour service is very helpful, and that uses multicast. Very, very helpful. It says, "Hey, everybody, I'm here." Thanks. Appreciate that, Apple. So it sends to a multicast address in v4 and v6, which is even helpfuler. Is that a word? Right. Right. So I'm getting everyone's DNS, delightfully advertising the existence of the host and the host name. We'll see it. It's cool. I hope no one has a really, really poorly named machine. Every once in a while, you get something like that. SMB and NFS also useful because they tend not to be allowed through security perimeters. So if you're seeing NFS, if you're seeing SMB, you can have a fairly good high confidence that these are local machines. So part of what we want to do is we want to make sure we filter out general hosts that are on the internet as not, these aren't my local machines. So you have to come up with a strategy for doing that. It's often as simple as using RFC 1918 prefixes. 192, 168, 172, 16. You can just filter on those. But keep in mind, an intruder, especially a malicious intruder, may not follow your numbering conventions. Right? So you can't necessarily make an a priori filter that says, I'll just throw out the other things, because that's precisely what they're hoping you'll do, and not notice that there's just a random other IP address floating around your network. Force routing. But again, so if you know that your firewall has a rule, no inbound traffic from this or no outbound traffic from that, great. That's perfect. You can use that same filter as your pre-filter on your survey, because you know that nothing is getting in the other way. In that same address space. We're pretty good at doing IP address filtering. So again, if you own the firewall and you know the guy that owns the firewall, just grab the same set of rules and throw that on your filter and say, okay, great. We can at least make a simplifying assumption that it has not gotten through the firewall, so it has to be a local source address. Good. Okay, so here's a simple example. We'll show you much more interesting examples in the demo. 15 minutes left. I like this little timer. That's cool. Yeah, there's like a thing up here. Right, so all this is doing is here's 1918 pre-filtering, CIDR blocks, and just showing you, here's really super simple. So source type equals stream : star, right? So anything that stream happens to see. We'll narrow that down a little bit in the demo, but real easy. And so these are in the slides that you guys can download, so you can grab these to start. And it's just showing you the stuff on my local network. I mean, how easy is that? It's 3 lines of SPL. Just turn on stream, turn on some of the default streams, and boom, you start seeing what's on your network. Great. That's a good way to go. Right? But then how do you look at services? Well, fortunately, you can use that list once you've collected it as your limiting list to say, all right, well, we know that these hosts exist. We can start by using that as a list to pre-filter on services. Or if we want to. We don't necessarily have to do that. But again, you want to look at services. And there are really two ways to look at services, one better than the other. You can look at destination ports, right? So again, we can make the simplifying, and I think fairly reliable assumption that if a machine has a connection that has more than 0 bytes of data sent to it on a given destination port, that machine is listening on that port and has a service running on it. Now, if you're doing just port scans, that's fine, but you're not going to get anywhere past the TCP SYN. You're going to get a TCP SYN followed by a TCP reset, and that's it. Maybe. But you're not going to get any data bytes, right? So if you see some data on a TCP connection to a machine that you own, you can make, I think, a fairly high probability assumption that that machine is running a service on that port. So if all you know, and if all you have, if you're not doing this with Stream, but if you're doing this with something else, because this entire philosophy can be done with any data that you have. If you have IDS data, you have Bro data, you have Snort data, you have anything that's giving you this same information, you can do this. So this whole philosophy doesn't require Stream, but we'll show you one of the useful things that Stream does in a second. So again, you can use internal server ports. I used to go through this list and make people name the ports, right? UDP 514, UDP 53. No, I don't want to do that game. We have more important things to do than play. Who knows their RFCs? But again, so just a little more interesting. All we're doing there is adding a heuristic, and it's an assumption, but it helps because often you'll get destination and source port mixed up. So notice that where clause in the middle, where source port is greater than or equal to destination port, and where destination port is not equal to 0. So making sure that the connections aren't reversed, which sometimes they are. We're just saying, all right, assume the ephemeral port is the source port, and the non-ephemeral port is the destination port, and the destination port is lower than the ephemeral port. Not actually necessary, but in this case, it just sort of helped drown out some of the noise. So again, here what we're doing is we're taking that same list of hosts that we gathered in the first step, and now we're inspecting the services that we're running, not actively. That is, we're not doing a port scan on those machines. We are not doing it by putting an agent on those machines and doing a netstat minus NAO pipe grep listening. Why do I know that offhand? Right? But instead, we are looking at actual traffic sent to those machines. Now, is this going to be an exhaustive list? No, because we're not polling the machine, because we're not on the machine. There are going to be things that we miss. So there's going to be false negatives, right? So we have missed some things. We know that right off the bat. But there are going to be no false positives, which is great from our perspective, because how many times have you had to chase down a false positive? That stinks. This is useful because there are 0 false positives. If there exists a connection in this list, that connection is being used by somebody because we saw it. How useful is that? Okay, I think that's the end of my slides. Awesome, okay. Through the slides and, 10.5 minutes left. Okay, pushing the demo button, fingers crossed. Okay, cool. All right, so this is Stream, and again, about half of you are familiar with Stream, so I'm not going to go into too much detail on Stream, but I'm going to show you briefly. I set up 3 new streams. They all have the word survey in them. So here is TCP survey, here is UDP survey, and here is IP survey. I'm just going to click on TCP survey, and I will zoom in a touch so you can see it from the back. All I'm doing is basically grabbing. Maybe zoom out just one more. Okay, that's it. Those are all the fields I'm grabbing. So if you look at it, really it's just the descriptive information for the packets at layers 3 and layer 4. So IP addresses, ports, some metadata and statistics. So byte count, packet count, this really, really useful field called protocol stack, and this equivalently useful field called app. That's pretty much it. I haven't done anything with canceled, anything with TCP status. And the other protocols are all similar to that. So we have TCP survey, UDP survey, and IP survey, right? And so I could just go into search and reporting and just give me super simple, something like source equals star, or stream, because everything starts in stream starts with stream, colon star survey, pipe head, 100, and boom, now there's 100 events, right? So that's all of my stream data. I think I've only been doing this for about 4 hours. I turned this on around 2 when I walked down to the conference center, right? So what we might want to do is, I'm going to filter out my personal machine because we know there's going to be lots and lots of traffic to it. And if I remember correctly, it is, .121. So, okay, great, we're getting rid of that. So I can then just do something like stats count by source IP, dest, IP, and app. And that's the last thing I'm going to type, and then I have a bunch of reports. But look, we have 794 hosts that we have collected. Actually, that's not true. We have 794 unique combinations of source, dest, and app. Here, let's do a authentic list. So here, 432 unique source IP addresses in 2 hours since I turned the thing on. That's useful, right? And keep in mind, I am not on a span port. I am not on a gigamon. I'm not on a packet broker. This is just stuff I saw on my stupid laptop with nothing else. Right? I mean, this is the absolute easiest thing I can possibly do with a regular off-the-shelf Mac. This is not a Wi-Fi pineapple. This is just a commodity Apple machine, right? All right, so let's look at a couple of the reports I built. So, for example, the first thing I did was, remember I said we're going to harvest. So I have a harvesting search that runs once a minute. Now, normally you wouldn't run this once a minute. I just wanted to kind of seed it quickly. It's a little bit difficult to read. Ironically, the comments were there to make it easy to read, and they end up making it much more difficult to read. And this is not Windows logs, it's stream logs, because we did change that. But all right, so what is this doing? This is simply saying, read from stream, and then grab machines and compare them against an input lookup. So one interesting question is, what happens if you do an input lookup to a file that doesn't exist? Nothing. That means it's totally fine. It just gives you a null result, and you can proceed merrily along your way. Great, no errors. So you don't even have to seed this file. You don't even have to create the file. Simply run this search once, and you get a survey. And I'll show you what that looks like. And this file is called here, known_dvc.csv, right? So known devices.csv. I'm going to do this right now in front of you live. I'm just going to say, all right, input lookup. And boom, there you go. Okay? So what this, and that file started at blank 3 hours ago when I turned it on, 2 hours ago, whenever I turned it on. So what it's doing is, it is taking, and this is the really important bit of this append equals t. So it is running a stats across the data that I collected, and all it is looking at is source address, nothing else. And saying, all right, simply update the earliest time and the latest time using the stats command. Earliest and latest are new stats functions you can run, and it will literally just give you the earliest and latest versions of underscore time. You combine that with the append in the input lookup, and then run the stats again. That's the important thing, because then it combines the previous list with the new list. And now you have a new composite list that has new stuff and old stuff all mixed together. But it has updated the things like the last seen count and the hit count. So now your new list, which is stored in the CSV, has been updated. Now this search is running once a minute, right now on this machine. We're not in the cloud, it's doing it literally right here. And it's doing it on that stream data we saw just a minute ago. So a nice easy way to look at it is, I can just go over here, let's see, I have survey host file open. Here, let's just click on that. I didn't mean to do that. And I can simply sort it by first seen, right? So these are the actual machines that are running in the network. And you see most recently, This one was collected 17:23:55, which is like a minute and a half ago. But also notice the last seen numbers, right? So you can say, hey, look, this one was, this example, 159 was seen at 17:14, but originally, but it was most recently seen at 17:23. So this is really useful for a couple reasons. Number one, it's super easy to find new things because they're already in the file. You just say, well, show me the things that have been seen in the last minute, hour, day, right? You could do this once a day. Like the customer I have this demoing at right now, he gets an email once a day that says, here are the new hosts we saw yesterday. That might be useful, right? And then he grabs an intern and says, go find what these machines are. And the intern spends the day tracking down those machines and kicking people in the head and whatever, right? And saying, why didn't you report these machines? Why did you just connect a new machine, right? But every day he gets a little report, and on the good days are the days that email is empty. And it happens, but more often than not, that email is not empty. Right? Another thing you can do, stale machines. Right? If we go back this way and we look at the first one and we see oldest, right? Last seen long time ago. Right? We haven't seen it since the original, the first time we saw it. Whoops, did I click the right? Here we go. So 1723, 1438. Oh, wow, we haven't seen this one. This machine we saw once. Oh, and look at this. This machine is not even on the 10 network. Remember what point I made earlier? Just because you are on an RFC19 source address network doesn't mean that the machines will obey that convention. Right? So there's a machine that shouldn't be on this network, and yet we saw it 6 times. What is it? Why is it there? I have no idea. But the first part of any security investigation, if you're doing security, and you grab this and you pull in the security people, is discovery, right? We need to know what's on our network. So we just discovered something. Now you grab a security guy and say, go figure out what this is. Great. Same thing for applications, right? All of these hosts have applications. Now I didn't put this in the survey, but it's very easy for us to do that same exact function with the survey by simply saying, all right, show me the apps that those hosts are running. And again, you get the protocol, the full protocol stack. So as I said, most of these are going to be, oh look, Spotify. Interesting. Right, so we can take this search here. I have like a minute and a half left. I can take this search here and just add, well here, let's just add stats, oops, or top app. Interesting. Steam, who is gaming? Come on, really? I mean, I know yesterday people were watching the game, but people are actually doing gaming on the Splunk network? Well, one guy, all right, or gal, sorry. Really, is it that fast? Is the network fast enough to support Steam? But okay, I mean, cool. Spotify, not that terribly unexpected. I could listen to some music myself. NetBIOS, okay. All right, I mean, that's cool. It's interesting, right? So again, we're learning about the network, about what's going on in the network, about resources on the network. And all of this is really important because if you don't know what's on your network, you're not going to be able to do anything useful for it or to it. Right? So what are our takeaways? Wire data can clearly be used to discover hosts and services. We just saw it. And I hope no one was embarrassed and that their machine popped up there. I hope that didn't happen. And Stream can provide layer 7 data to help facilitate discovery because all of those app tags came from Stream. Right? So if you have Stream, if you're just using general wire data like NetFlow, you can do this, but you're going to get destination ports. Okay, good, better than not, right? But if you have Stream, it's going to give you on top of destination ports, it's going to give you application identification, which is, as we just saw, super useful. All right, that's it. Thank you very much.